So, hmm, okay, we move towards the next chapter of system calls. So, syllabus for this chapter is open. First point is open, then read, write, lseek, close, file creation, change directory and change root, change owner and change mode, stat and fstat, def mounting and unmounting, link and unlink. These are the different system calls regarding the file d- uh, regarding the file or block allocation. So such as open file, read file, write file, close file, file creation, change directory of file, change root of that file, change owner of that file, change the mode of that file, then mount, unmount that file, link, unlink of that file. So these are the system calls regarding the file system. So all these system calls covered in a book. So for this chapter, a textbook is a design of Unix operating system by MJ Batch. Then CO will be student will be the implement all system calls related to the file system. So our title of this chapter is a system call. What is the meaning of this title? Our system call is just what it is. Name implies that it is a request for operating system to do something on the behalf of users program. The system calls are functions you used in the kernel itself to the programmer. The system call appears as a normal C function call. Then what is the central idea of the chapter? The system call provides a services of the operating system to the user program via application program interface, that is API. It provides interface between process and operating system to allow user level processes to request services of operating system. The system calls are the only entry point to the kernel system. Then importance of the chapter in the syllabus. So in computing, a system call is a programmatic way in which a computer program requests a service from the kernel of the operating system it is executed on. A system call is a way for programs to interact with the operating system. A computer program makes the system call when it makes a request to the operating system's kernel. The system call provides the services of the operating system to the user programs via application program interface, that is API. It provides an interface between process and operating system to allow user level processes to request services of the operating system. System calls are the only entry points into the kernel system. All programs needing resources must use system calls. So, what is why this chapter included in the syllabus? So, different services provided by system calls, such as process creation and management, main memory management, file access, directory and file system management, device handling, input output, protection, networking, etc. Then types of system calls, there are 5 different categories of system calls, that is process control, file management, device management, information maintenance and communication. So out of them, process control consists of end, process abort, process create, terminate, allocate, and free memory. Similarly, in case of file management, create, open, close, delete, read file, etc. So in this chapter deals with the system calls for file system using the concept explored as a previous chapter. It starts with the system calls for accessing existing files such as open, read, write, lseek, and close. Then presents a system calls to create new files, namely create, mknode, that is make node, and then examines the system calls that manipulates the inode or that maneuver through the file system, such as change directory, change root, change ownership, change mode, stat and fstat. It investigates more advanced system calls such as pipe, dub are important for the implementation of the pipe in shell, mount and unmount, mount and umount extended to the file system tree visible for the users, link and unlink change the structure of the file system hierarchy. Then it presents the motion of the file system abstractions, allowing support of various file systems as long as they conform to the standard interfaces. And last section of this chapter will be cover system maintenance. This chapter introduces a 3 kernel data structures, that is file table with one entry allocates every opened file in system, then user file descriptor table with one entry allocated for every file descriptor known to be a process, and mount table which contains information for every active file system. There is a figure on next slide which shows the relationship between the system calls and different algorithms which are described in previous chapters. We have studied in previous chapters. It classifies the system calls into several categories, although some system calls appear in more than one category. See, this is the figure with different system calls regarding different with algorithms. So out of them, we have studied the buffer allocation algorithms such as get block, buffer release, buffer read ahead, and buffer write algorithms in second chapter. Then third chapter, that is previous chapter, we have seen I get, I put, then I alloc, I free, alloc free, and bmap algorithms. That is, this is lower level file system algorithms. Now, in this chapter, we are going to study the different system calls. So, in case of file descriptor tables such as open, create, dump, pipe, close, these system calls are used. Use of name I algorithm with the help of these system calls such as open, create, change directory, change root, change ownership, change mode, stat, link, unlink, mknode, mount, unmount. Then whenever you should have to assign inodes, then there are system calls such as create, mknode, link, unlink. Then file attributes, there are different attributes such as change ownership, change mode, stat. Then file input output, there is a read, write, and lseek system calls. Then file system structure, for this structure mount and umount. And then tree manipulation, for tree manipulation, change directory and change ownership, these system calls are used. So system calls, what are the system calls? System calls that return file descriptors for use in another system call. System calls that use name I algorithm to parse a path name. System calls that assign and free nodes using algorithm iloc and ifree. System calls that set or change the attributes of file. System calls that do input output to and from the process using algorithm iloc, free, and the buffer allocation algorithms. System calls that change the structure of the file system. System calls that allow process to change the view of the file system tree. So system calls are used regarding different purposes. So first system call is open. So open system call is the first step process that must take access data in a file, and the syntax is for open system call is fd, that is file descriptor. Fd is a file descriptor is equal to open, then the parameters as path name, flags, and modes, where path name is a name of file or file name, flag indicates the type of open, such as for reading purpose only or for writing purpose only. That is, these flags for read mode or read only mode or write only mode. And the third mode gives third parameter, that is mode, which gives file permission if the file is being created. So the fd is a syntax. Fd is equal to open, path name, flags, and modes. The open system call returns an integer called the user file descriptor. Other file operations such as reading, writing, seeking, duplicating the file descriptor, setting the file input output parameters determines the status, and closing the file use the file descriptor, that open system call. These are the different file operations such as read, write, lseek, duplicate, or seeking. These are the different parameters or different file operations. So for open system call, the syntax is fd is equal to, that is file descriptor is equal to open. Then parameters are path name, flags, and modes, where path name is file name, flags indicates the type of file, type of open, such as for reading or writing, etc. And mode, it gives the permission if the file is being created. Then this is algorithm for opening a file. So name of algorithm, that is algorithm open. Input for this algorithm is file name, that is a type of open. File permission, then for creation type of open, and then output, that is file descriptor. So convert the file name to inode by using the algorithm name I. If the file does not exist on the permitted access, then return error. If the file does not exist or not permitted access, then return error. Otherwise, allocate file table entry for inode, initialize count, offset, allocate user file descriptor entry, set pointer to file table entry. If the type of open specifies truncate file, if type of open specifies truncate file, free all file blocks with algorithm free, unlock inode with algorithm name I, then return, that is user file descriptor as a output. So once again we will see algorithm open, input, that is file name, then type of open, then file permission, that is for creation type of open, then output is fd, that is file descriptor. So first convert the file name to inode using the name algorithm. If file does not exist or not permitted access, return error. Otherwise, allocate file table entry for inode, initialize count, offset, allocate user file descriptor entry, set pointer to the file table entry. All the types of, if type of open specifies truncate file, free all file blocks using free algorithm, unlock inode using name algorithm, and return as a fd file descriptor. So kernel searches the file system for file name parameter using name I. It checks the permission for opening a file after it finds the in-core inode and allocates an entry to the file table for the open file. The file table entry contains the pointer to the inode of the open file and field that indicates the byte offsets in the file where kernel expects the next read or write to begin. The kernel initializes the offset to 0 during the open call. Initially, the offset is 0 during the open call, meaning that initial read or write starts at the beginning in a file by default. Alternatively, a process can open a file in write append mode. Alternatively, a process can open a file in write append mode, in which case kernel initializes the offset to the size of the file. The kernel allocates an entry in a private table in the process user area called user file descriptor table and notes of the index of this entry. The index is the file descriptor that turn to the user. The entry in this file table points to the entry of global file table. See, this is the user descriptor table, that is U file descriptor table user area. Then this is the file table and this is the inode. Here three files are opened, fd1, fd2 and fd3. So file open, name of that file is etc password. Open, name of that file is etc password. Then purpose for that file, only, O for only, rd for read, read only, open, read only. So etc file, here everyone is at user descriptor table location 3. Here count 1, it is open for read only. File table contains, this is count 1. Then go to the count 2, that is inode table. Then fd2 file descriptor 2 open, that is name of this file is local. Then then rd for read and wr for write. So read and write purpose you should have to open. Here user area contains file number 4. Here read and write and go to the inode table where it is stored, that is count is 1 and local, name of the file is local. Then open, again etc password file is opened. So this file is opened two times. In first descriptor table, it opened for read only, and in second descriptor table, here a third descriptor table opened write only. So at fifth location, so count 1 for write, here count 1 for read, here count 1 for read and write, and here count 1 for write. But same file is opened etc password two times for reading and writing. That's why here count is 2. Here count for local one is 1 because it is opened file is only one time. Here the same file is opened for different purposes, but same file is opened two times, so here count is equal to 2. So this figure shows the relationship between inode table, file table and user descriptor data structure. So each open returns a file descriptor to the process and entry corresponding entry in the file descriptor table points to the unique entry in the kernel file table, even though one file etc password, here in this example we have opened twice. So table entries of the all instances of an open file point to one entry in a core inode table. The process can read or write the file but go only through the descriptor 3 and 5. So this file is opened at the location descriptor table location number 3 and location number 5, the same file is opened. So kernel knows the capacity to read or write the in file in the file table entry allocated during opening the file. So suppose second process, suppose second process, that is fd1 open, name of file is etc password, read only, and open private, read only. So see in this figure, see there are two processes, process A and process B, for user file descriptor table, then file table, then inode table. So see here, file opened for reading purpose, so count is 1, for read write count is 1, then for reading purpose again count 1, for write and read count is 1. But here see in inode table there is count 1 for local, count 1 for private, but count 3 for password. So because this file is opened 3 times, first is opened for reading, second time is opened again reading, and third time opened for writing. So two times is 2 times this file is opened, password file is opened 2 times by the process, once one time by process A and other time by process B. So number of processes can open the same time. Okay, so this figure shows the relationship between appropriate data structure while both processes have opened the file. Again, each open call results allocation of unique entry. Each open call allocates the unique entry in the user file descriptor table. Here, see in user file descriptor table, in each process there is unique or single entry. There is a single entry, but kernel contains at most one entry per file in the core table. So user file descriptor table entry could conceivably contain the file offset for the position of next input output operation and point directly to the in-core inode entry for the file, then eliminating the need for separate kernel file table. So this example shows one-to-one relationship. Here, see process 1, for process A, opening, that is open the file for reading purpose, open the file password for reading purpose. Here one-to-one relationship between user file descriptor table and kernel file table entries. See here, these are user file table entries and these are the kernel file table entries. Here one-to-one relationship, and the first three file descriptors, these first three file descriptors, that is 0, 1 and 2, are called as standard input, standard output and standard error file descriptors. These three file descriptors, that is 0th is a standard input, this first is standard output, and second is standard error. The process on Unix system conventionally use standard input descriptor table. So the use of standard input descriptor to read input data, the standard output descriptor to write output data, and standard error descriptor to write error data. So for reading input, we can use a standard input. For writing output, we can use a standard output, or for giving us errors or error message, we can write the error data with the help of standard error. Then next command or system call is read. The syntax of read system call is number is equal to read fd buffer count. Fd buffer and count, these are the parameters of the read system call, where fd is a file descriptor turned by open. Fd is file descriptor turned by open. Buffer is the address of data structure in the user process that will contain to read data on successful completion of the call. Count is the number of bytes of the user wants to read, the number of, and the number is the number of bytes already read. Here number is mentioned. Here number, it is the number of bytes actual read. Fd is file descriptor table, file descriptor returned by open. Buffer is the address of data structure in which user process that will contain read data on successful completion of the call. Then count is the number of bytes the user want to read, and number is the number of bytes actually read. The kernel gets the kernel gets the file table entry that corresponds to the user file descriptor following the pointer. So there is a algorithm for reading a file. So algorithm read, input for this algorithm is user file descriptor address to buffer and user process number of bytes to read. So input for reading a particular file. So FD provides the buffer address in user process number of bytes to read. Then output count the number of bytes copied. Count the number of bytes copied into user space. So while getting file table while getting the file table entry from the user descriptor, you should have to check the file accessibility. Then set parameters in user area for user address, byte count, and input output to user. Get inode from the file table, lock inode, set byte offset in user area from the file table offset. While count not satisfied, if it is correct or if it is true, then disk block convert file offset to disk block by using bmap algorithm. Calculate offset into the block. Algorithm for reading a file. Algorithm read input, that is user file descriptor, address of buffer in user process number of bytes to read, then output count number of bytes copied into the user space. So get file table entry from the user file descriptor, check that file have accessible permission. If it have accessible permission, then set parameters into the user area for user address, byte count, and input output to user. Get inode from the file table and lock inode. Set byte offset in user area from the file table offset. While the count is not satisfied, if it is true, then convert the file offset to the disk block by using BMAP algorithm. Calculate the offset into the block, number of the bytes to read. If the number of bytes to read is 0, that is end of file. If it is 0, that is go out of loop, that is break this loop. If number of bytes to read is more than 0, then read block with the help of be read ahead algorithm. If the read ahead or with the help of algorithm be read, copy the data from system buffer to user address, update user area fields for the byte offset, read count, address to write into user space, and release buffer with release that buffer which is locked in be read. If this condition is not satisfied, that is count is satisfied, then this condition becomes false. Go out of loop, unlock inode, update the file table offset for next read, and return total number of bytes read. This is algorithm for reading a file. It now sets several input output parameters in user area as shown below table. See this table. There are different mode that which indicates read mode or write mode or execute mode. Then count of bytes for reading or writing. Then offset byte offset in a file. Address to target address to copy data in user or kernel memory. Then flag indicates if the addresses is in user or kernel memory. So specifically it sets input output mode to indicate that a read is being done, flag to indicate that input output will go to user address space, a count field to indicate the number of bytes to read, the target address of the user data buffer, and finally an offset fields to indicate byte offset into the file where the input output should be. After that, kernel sets the input output parameters in the user area. It follows the pointer from file table entry to the inode, locking the inode before it reads the file. The algorithm now goes into the loop until a read is satisfied. The kernel converts the file byte offsets into the block number using algorithm BMAP, and it notes the byte offset in the block where in the input output should begin and how many bytes in the block it should read. So after reading the block into the buffer, possibly block a read ahead algorithm, that is B read algorithm or B read ahead algorithm we have seen in previous chapter, which copies the contents from the block to the target address of user process. It updates the input output parameters in the user area according to the number of bytes it read, incrementing the file offsets, incrementing the file byte offset and address in the user process where the next data should be delivered, and decrementing the count of bytes it needs to read to satisfy the user read request. If the user request is not satisfied, the kernel repeats the entire cycle, converting file byte offset to the block number, reading the block from the disk of a system buffer, copying data from that buffer to the user process, releasing buffer, and updating the input output parameters in the user area. The cycle completes either when kernel completely satisfies the user request, when the file contains no more data, or if the kernel encounters an error in reading the data from the disk or in the copying the data in user space. The kernel updates the offset in the file table according to the number of bytes it actually read. That is, conversely, we can say successive reads of a file deliver to the file data in sequence. This is a sample program for reading a file. Here, integer file descriptor, that is FD, then character little buffer with size at 20, then big buffer with size at 1024, then FD is equal to open, the file name is etc password, and read only, then read the file buffer